Good evening. Today we will go over double integrals over general domains. So we introduced the concept of a double integral for the domain in the shape of a rectangle, and that meant the bounds of integration for both variables were constants. So remember, a rectangle domain essentially means that the bounds for the two variables of integration are just given by constants. And so we concluded from in that section that you can switch the order of integration however you like. So you can integrate with respect to x first, or with respect to y, or vice versa. So that's essentially the Fubini's theorem, which computes the double integral as an iteration of two Riemann integral in the variables x and y. What we achieve in this section today is kind of the same thing. So the title, to be more precise, should have been named as double integrals over more general domains, because as it turns out, you still need certain conditions on the domain, but the point is that we can compute these integrals over domains that are not so just more general than just a rectangle, which is a good thing, obviously, because most of the domains encountered in real life are not exactly in the shape of a rectangle. So the result of Fubini's theorem is the same, in the sense that under some conditions we can change actually the order of integration, but we have to be a little bit more careful in this case. First of all, it is not always the case that we can actually do that, and even if we can do interchange the order of integration, the bounds may change. It's not just a matter of flipping the two integrals. You need to actually re-evaluate the actual bounds of integration. Okay, so enough with the preliminary, so let's get into the main topic. So there are two types of domains for a function of two variables, f of x, y, that we can integrate. That is to say that we can compute a double integral over. Kind of uninspiring, these two types are called type 1 and type 2. So I think it's best to actually sketch them and then explain the main properties. So the type 1 domain that we can integrate looks like this. The domain is in between two vertical lines over x. So the left and the right bounds are still constants. But the other bounds for y could be given by some generic functions in terms of x. So for example, you can have something like this. So this is the domain, and the lower bound for y is given by some curve, y equals f of x, and the upper bound for y is given by some curve, y equals g of x. So in order to understand what you need to actually, what type of domain you need to have in order to be able to integrate, basically you should be able to slice your domain either with vertical lines, like it is the case in the type 1 domain, or horizontal lines, as you'll see in a minute in the type 2 domain. So mathematically that means, what does it mean to actually be able to slice it with vertical lines? So each slice should be basically described by the same bounding function. So if I take a typical slice in the middle, it should correspond to a variable with constant bounds. So indeed x is between a and b, and the top and the bottom, the other bounds of the slice, should be in terms of two functions in terms of x that are the same for each slice. So if I move the slice from left and right, the bounds of the other variables are given by the same functions. Lower bound is f of x, upper bound is g of x. So not to overcomplicate things, more general domains in the context of this section simply means that two of these four bounds, or in other words, one of the pair of bounds, can be in terms of a function of the other variable. We cannot have just general bounds, like all four of them. You still need basically two constant bounds. usually in class, I think I'm going to skip this because I don't think it's going to look nice on the online version of the course. But usually in class, I actually try to sketch a 3D picture. And I'll show you the reason why we need these conditions, basically. It has to do actually with how we define the double integral. You know, you can interpret it as a volume. Basically, these slices that I mentioned here in the domain correspond to three-dimensional slices of the volume, which basically is representing the double integral. And the type 2, it's the analogous stuff over the y-axis. So the type 2 domain that we can compute a double integral will require two constant bounds for y. So not to use the same variables, constants here, let's say c and d. And the left and right bound for x can be given as functions of y. So this one, for example, is, let's say, x equals f of y. And the other one is, let's say, x equals g of y. So if this is the domain in question, again, you can basically describe the domain by slicing it horizontally, with each slice defined by a variable with constant bounds, y in this case, between c and d, and the bounds for the x coordinates given by the same functions, left and right. Okay, f of y less than x less than g of y. So a domain suitable for integration, double integration, type 1 or type 2 can be described in words. So that means it's going to be your job to figure out these bounds. That's the tricky part sometimes, that you have to be really careful and go slow. Or it can be given already in terms of these equations. Like I said, typically the hardest types of problems are when the domain is described by some enclosure and you need to figure out whether it is type 1 or type 2 and how these bounds are set up. Setting up the bounds and the integral is the most important part to go slow. Once you set up the integral, then of course you can either use Maple or by hand, depending on the case. All right, so Fubini's theorem states the following. For a type 1 domain, it states that the double integral, let's actually write it in one single formula. The double integral over, well, actually, let's write it twice. So the double integral over this domain, if it's type 1 domain, is going to be with the outermost integral given by the constant bounds. So pay attention here, it's very important, okay? So the outermost integral is the one for the variable with the constant bounds, x in this case. And the innermost integral is the one with the variable bounds in terms of x. So f of x, g of x. Let's actually call h the actual function to integrate, because I use f and g for the bounds. So h of x, y, dy. So if it's just a type 1 domain, or if you view it as a type 1 domain, it's very important to use the correct order of integration. Outermost integral, constant bounds, innermost, the other integral in terms of x. Finally, if it's a type 2 domain, as you can guess, your double integral will have the constant, the outermost integral in terms of y, because that's the one with constant bounds, and the innermost integral in terms of the bounds for x. So f of y to g of y, and h of x, y, dx, and again the outermost integral dy. Alright, so this is the Fubini's theorem that you should write on your formula sheet. And again, feel free to also sketch, you should sketch also the type of domain we're talking about. So you should include at least this inequality, if not the actual picture of the domain, right? And so an important remark, some domains can be viewed as both type 1 and type 2. And that's a very good thing indeed, which I'm going to focus on the next examples. Because this property that they can be both of type 1 and type 2, this allows you to change the order of integration. Dx dy versus dy dx. And that's a very good thing. I mean, if you do it with a computer, that you don't care as much, but by hand it matters quite a lot often. Not always, but often, because sometimes one direction may be easier than others. Okay, so let me think a little bit if it's worth actually squeezing in this stuff here. Okay, so I don't think so. We're gonna, well, actually let's sketch a couple of domains and we're gonna start examples on the second page. So here's an example, and I'm gonna sketch this, yeah, so here's an example of domains which can be treated as both type 1 and type 2. So let's say you have something like that. We're gonna use an example like this on the next page. Like a domain between a parabola and two lines, horizontal and vertical. Okay, so in this case, notice that once I know the bounds here, I can treat this as a type 2 domain, like going by the y coordinates on the outside between two bounds, or I can view it as a type 1 domain by slicing it over the x coordinate first. Again, we're gonna do that with an example to make it clear. So you can have constant outer bounds for x on the outside and inner bounds in terms of x, constant outer bounds on the outside for y, and inner bounds in terms of x in the inside, in terms of y on the inside. So obviously there are domains which are neither of the two. Most of them in this, I mean, many of the domains we're going to encounter here are probably most of them both of type 1 and type 2. And then the question is basically to just choose the right or the most appropriate order that gives you an easier time to compute the integral. Sometimes, by the way, actually, I should mention, it's not obvious which direction is easier, which only along the way you may realize that, oh, maybe I should try the other way around because probably it's easier. But here at least geometrically, how a shape that is not type 1 or not type 2 looks like. So for example, if you see something like this, let's say, okay, so notice this one can be viewed as a type 1 but not type 2, because notice if you do horizontal slices, not all of them will have the same bounds. So here you're going to have actually two pieces. So you're not going to have the same bounds. I mean, you're not going to have the bounds described by the same functions. So typically when you have these gaps, these are typical examples of domains that are neither type 1 nor type 2. What about this one, for example? Obviously, this one can be viewed as a type 2, right? You can have these horizontal slices, and each slice will have the inner bounds given by the same functions, this round, this curved, left and right, but it's not type 1, because vertical slices will not be given by the bounds given by the same functions, right? Like f of x, g of x. And of course, you can have neither of the two. I mean, you can realize that you can have this combination. Let me see if I can do it, kind of like that, right? So this is neither type 1 or 2. Now, what do you do with domains like this if you encounter them in life? Well, you can break them down. So you basically split the double integral into a sum of multiple integrals or double integrals, and then you break the domain into pieces that are either type 1 or type 2. This often is, of course, easier said than done, but that's one of the approaches you can do. All right, so let's go over examples, and we're going to spend until the end of the section, we're going to spend time on various examples. So stay tuned. All right, so let's go over our first example. Let me see here. Let's say the problem states find the double integral of x plus y dA, right? So the function to integrate is x plus y, where the domain D is the region bounded by the curves y equals x squared, x equals 0, y equals 4. This is the typical problem from now on. This is a typical integration problem that kind of has all the elements. It can be made easier. Like I said before, you can see the domain may be given already as a picture, or you already have the integral in terms of like with the bound specified already, which makes it easier. But let's start with a typical one to see actually what you're supposed to do. Again, as I remarked, you don't want to go fast on this section, so I can't emphasize this enough. You have to take enough time, as much as needed, maybe 2 hours, to really go slow in order to understand the main approach. Don't rush to integrate. Typically, that's the easy part. I mean, easy if you know how to integrate, obviously, but the setup is what you really have to grasp here, because that's the really new calculus 3 specific part of the problem. So you need to visualize the domain, carefully sketch it, carefully find possible intersection points that you may need, decide over the type 1 or 2, and if it's both, of course, pick one and then set up the integral and then worry about how to compute it. This will be both of type 1 and type 2, so just for practice we're going to do it both ways. You don't have to do that, obviously, but just to see how it works. Okay, the domain may be described by a bunch of curves. There's no specific number of the curves, right? It could be 2, 3, or more. The idea is to sketch each of them and then see which region all of these curves will enclose, and that's going to be the domain. Again, very carefully, because it's very easy sometimes to actually mistake a different region than the real domain here. So we're going to do x equals 0, well, y equals x squared, x equals 0, y equals 4. Now, x equals 0 is just the y-axis. Y equals 4 is a horizontal line, like that. Okay? Y equals x squared, and actually, to be absolutely correct, because I wanted to just the right half, and let's state also that I want x greater than or equal to 0, so that I exclude the left side. I don't want to put the left side in the left of the y-axis. Okay, so y equals x squared with x greater than 0, it's this branch of the parabola. I should have made it a little bit faster, increasing upward, but as long as you label the points correctly, that's all fine. So notice, right, and by the way, notice the domain enclosed by these 3 curves. Once again, x equals 0, let's emphasize it. Y equals 4. And then the parabola. Let me make it a little bit thicker like that, because I don't want to fill in the domain here. All right, so I think it's clear what the domain is. Notice right off the bat that the intersection point here is probably important. Why is it important? Well, what if I wanted the bounds for x? What if I want to integrate with respect to x on the outside? I'm going to need to find those bounds, which means that I need to find the intersection point between the curve y equals 4 and y equals x squared. I need the intersection point, which means that you may have to solve these little 2x2 systems in order to find the intersection point. In this case, obviously, you can do it in your mind even, because how do you solve this quick system, I mean, you can set this equal to each other because both of them represent y. I want x greater than 0, so x is equal to 2. All right, so the left bound here is 2. Just by looking at it, you realize that it can be treated as both type 1 and type 2. So let's set up the integral as a type 1 double integral. Type 1 means constant bounds for x on the outside. All right, so the next thing you do, once you decide it's type 1, draw a typical vertical slice. A typical one in the middle, not one like further to the left or to the right, okay? Not x equals 0, x equals 2. Those are part of the domain, but you want a typical slice corresponding to a typical x coordinate between 0 and 2. All right, so that means the outermost integral is between 0 and 2. Okay, and here's the part that people get confused with. Once you decide that these are the outer bounds, the other variable will have the outer bounds in terms of two functions in terms of x. Now keep in mind, these guys may be constant. Usually not both of them, because if both of them are constant, you're going to have a rectangle. But in general, both of them could be constant. Both of them could depend on x, but sometimes one of them can be a constant. The thing is, in the type 1 setup, the bounds for y should be in terms of x. So you pick the lower bound, and you get y by itself if it's not already in terms of y, in terms of x. So what is this point as y equals f of x, or as a function of x? Well, it's already given, right? So x squared is going to be my lower bound for the innermost integral. Okay, so that's the lowest value of y. What is the highest bound here? That sits on a horizontal line. The outermost, upper bound for y, while in general it can depend on x, in this particular case, happens to be a constant. Okay, outermost, innermost integral. And so now you can set up the Fubini's theorem and compute the integral slowly and steadily. So we want a double integral of x plus y dA, which via Fubini's is the integral from 0 to 2 on the outside, from x squared to 4 on the inside, x plus y, in the order dy dx. Right? So dy first. Pause if you want and can try to do it on your own and then check with me. We're going to do integral with respect to y. So at this point x is a constant. So I'm going to have x times y plus y squared over 2 with the bounds for y given by x squared and 4. Once I plug in those bounds, then the result is going to be integrated with respect to x. So again, it's lots of room for computation error, so go slow. Plug in 4 for y. I end up with 4x plus 16 over 2. That makes it 8. Plug in x squared for y. That's x times x squared. That makes it x third. Plus, pay attention here, y squared. If y is x squared, that makes it x fourth dx. Finally, now we integrate with respect to x. That's going to be 2x squared plus 8x minus x fourth over 4 plus 1 over 2 x fifth over 5 between 0 and 2. When we plug in 0, there's nothing, so we just plug in 2. And so we get 2 times 2 squared, that's 8, plus 16 minus 16 over 4 makes it 4, plus 2 to the 5th, which is 32 over 10. 12 plus 8, 20, plus 32 over 10, and 1 second. There's a minus here, sorry about that. Minus 32 over 10. And then that makes it 200 minus 32 over 10. And that's 168. We can simplify by 2, and that's 84 over 5. Final answer. So normally you're done. But again, let's see how we establish the integral as a type 2 integral. We don't have to do it for this one, but just to see that you do indeed get the same answer. So going all the way back to the picture, type 2 means that I start with constant bounds for y, horizontal slices. Look at a typical, again, go back to the figure, a typical horizontal slice in red. So that means the outermost integral will be between 0 and 4 for y. This is the outer integral. And here's again, pay close attention here, go slow. Innermost integral should be like this. X between two bounds that depend on y. Just like before, one of them may be a constant. Sometimes both of them are in terms of y. Sometimes one is a constant, usually not both of them. Again, if both of them are constants, well, I mean, they can be constants, but that'll be rectangles. So we know how to deal with that. So your job is to look at the bounds as a function of y, that is to say x in terms of y, x in terms of y, f of y, g of y. The leftmost bound is 0, right? So what's the value of x here on the left, on the leftmost bound for that slice? That's going to be 0. So x in my case is greater than or equal to 0. And finally, on the same parabola, which remember is given as y equals x squared, right? On that same parabola, what is x as a function of y? That's the moment when you look at the function and get x by itself, right? So sometimes you have to actually switch the function from y in terms of x to x in terms of y, depending on what you need, right? So for a type 2 integral, you need the same point on the curve as a function of y. That means it may mean solving for x in terms of y if it's not in that form already. Sometimes the bound is already given as a function of y, so that means you're fine. But again, pay attention, it's not going to be just x squared like before. It's whatever that point is as x equals something. In this case, square root of y. So changing the order of integration means recalculation of the bounds. Means recalculation of those bounds. All right, so that means in this case the same integral again is 0 to 4 with respect to dy, and then the innermost integral 0 to square root of y x plus y dx. I can tell already that probably this is going to be easier to compute because I have 2 zero bounds, which ought to make the calculation easier. All right, so first integration with respect to x. Now y is a constant, so I'm going to have x times y plus y squared over 2 with the bounds for x given by 0 and square root of y. Let's plug in square root of y into square root of y, into this quantity here. So if I plug in square root of y for x, that's like y times square root of y, which is y 1 plus 1 half, it's y to the 3 halves. And then square root of y squared, what did I do here? Because I do dx, sorry. I do dx. This is actually x squared over 2 coming from integrating x. Yeah, so integral of x is x squared over 2. integrating y with respect to x is yx, which is the same as xy. So that's good. All right, so then I plug in square root of y for x. That's going to be actually y over 2. Y over 2, and then dy. All right, so finally the integral in terms of y, that's going to be 3/2 plus 1, that's 5 over 2, so it's 2 over 5, y to the 5 over 2, plus 1/2 y squared over 2 between 0 and 4. Plug in 4, that's 2 over 5, 4 to the 5 over 2, plus 1/4 times 4 squared, and then minus 0. Square root of 4 is 2, to the 5 is 32, and then 16 over 4, that makes it 4. It's 64 over 5 plus 4, multiply by 5, 64 plus 20, 84 over 5. Okay, so I hope you guys are convinced that you get the same answer. We're gonna do, let's see, yeah, let's do another one in which, yeah, so we're gonna do another one in which we're gonna justify, in fact, that indeed the order of integration may matter. But actually, well, let's do another quick one in which both bounds, inner bounds, are in terms of the other variable. So no inner bound is constant. So stay tuned for more examples. Okay, so here's another one. Domain bounded by y equals x squared, x equals y squared. This is kind of a symmetric thing, you know, so actually whether you set it as type 1 or type 2, it's the same idea. Let's do it as a type 1 domain. So you have a vertical parabola mixed with a horizontal parabola. Let's actually do a bigger picture here. And then, so I'm going to exaggerate a little bit this shape so that it's easy to see. Okay, so this is y equals x squared. This is y equals x squared, and this is x equals y squared, right? The horizontal parabola. Okay, once again, we need an intersection point, right? But it's pretty obvious it's 1, 1, right? So here the intersection point is clearly 1, 1. This is symmetric. And the domain is in between these guys. So let's view it as a type 1 integral. Okay, so once again, that means we're going to start with constant bounds for x. That's the outermost integral. Immediately, you're looking for, you don't have to write this down, but just because we are in the beginning, immediately you're looking for bounds in terms of x for y. That means you really look like y equals f of x, y equals g of x, y equals something in terms of x. For the lower and then the upper bound. Be careful to look at the correct curve, right? So the lower bound comes from the vertical parabola here, open upward. It is already as a function of x. So the lower bound for y is going to be x squared. On the other hand, the upper bound comes from the horizontal parabola. You need to get y in terms of x so you can figure out that bound. So y is going to be square root of x. So the upper bound for y is square root of x. All right, I hope it's clear. So let's do it. Then the double integral will be from 0 to 1, and then from x squared to square root of x, function to integrate dy dx. Dy, that means x is a constant. We're going to have x squared y squared over 2 with y between x squared and square root of x. And now very carefully, let's plug in root x into y, like so. And then plug in x squared into y. All right, so don't forget to square it again, because it's y squared in the actual integral there. Sometimes people forget to do the second integral because they get tired with integration, right? We're not done with the integrals. So let's simplify this. Root x squared, that's just x. So x third over 2. Fourth 2x to the power 6 over 2. And then finally we integrate with respect to x fourth over 4, x 7 over 7 between 0 and 1. Plug in 1, that makes it 1 over 8 minus 1 over 14. Common denominator, 14 minus 8, that's 6. Over 8 times 14, we can simplify by 2. And then I get 3 over 56. Okay, in some problems, the order of integration matters quite a lot. And by the way, in some problems, it is your job to actually figure out the domain from the bound. So here's another problem that's slightly different. The domain is not described, but it is inferred from the actual problem. So as a remark here, or like a question mark, why order of integration matters. So what if you have, let me see, yeah, what if you have as a problem, find the integral from 0 to 1 and then from 0 to 1 second. I want to give it in the hard way first. I want to give it in a fun way first. So no, let's do it like that. What if I have the integral from 0 to 1 and then from x to 1 of the function x e to the power y third dy dx. Now, first of all, notice I didn't mention the domain, but the domain is inferred, right? So the double integral is already given in terms of a Fubini theorem, but it is in a form that's not really useful because you cannot integrate it in this way. So before we sketch the domain, notice here that the computation of the antiderivative of e to the y third dy is impossible. We cannot, there are no, so this is one of those functions that admits an antiderivative, right? Because it's a continuous function after all, but the antiderivative cannot be computed by traditional means, or it cannot be expressed in terms of elementary function. So it's not possible to compute exactly there's no way to compute this integral in the exact form with traditional functions. So integrating with respect to y first, it's bad news because we cannot do it. But let's look at the domain and maybe we can change the order of integration, and maybe if we do that, then we can actually solve it. So we can infer from the way the integral is set up. Remember, dy goes with the inner bounds. So look at the innermost integral. So that tells you, and actually let's start with the outermost integral. That tells you that x is between 0 and 1, that's the outermost integral, and for a given x, y is between x and 1. So in order to sketch the domain, look at the curves obtained by setting x or y equal to their respective bounds, because those are the curves which describe the boundary of that domain. Start always with the constant bounds. So let's sketch it here in this corner. So x is between 0 and 1. Let's say this is 0 and this is 1. Y equals x. It's the middle line here, diagonal. And then x equals 1. X equals 1 over here. Y equals 1. Okay, so let's recap. As a type 1 function domain, we have x between the constant bounds and a typical slice that represents the innermost integral goes from x to 1, right? So y equals x, y equals 1 are the innermost bounds. So in other words, this is the actual domain over here. Okay, but like I said, it's not useful to view it as a type 1 domain. Let's view it as a type 2 domain, which we can. It's both of type 1 and type 2. So therefore, let's slice this thing horizontally. By the way, when y equals x, the intersection point here is still 1, 1, 1, right? Because it's on the point y equals x. So we're going to start now with y as the outermost integral, which is again from 0 to 1. And we're going to compute the left and right bounds for y. For x, I'm sorry. In terms of y, right? So on the left, clearly x starts from 0. On the right, x starts from whatever x is in terms of y. So this is pretty straightforward, right? I mean, y as a function of x is y equals x. X as a function of y is x equals y. So the outermost bounds for x, the innermost bounds for x are 0 and y. So exactly the same integral, right, can be written now from 0 to 1 dy on the outside, and from 0 to y dx on the inside of the same function. So this is where the magic happens, because now how do I compute the innermost integral? Well, now the innermost integral is in terms of x. The bad boy here, e to the y third, is just a constant. You can actually move it out of the innermost integral. It's just the integral of x dx, basically. So e to the y third is a constant. The integral of x dx is just x squared over 2. And then the bounds for x are 0 and y. Of course, it's a textbook example. It's made to work. And the reason it works is because, well, if I plug in y for x, now it's going to be e to the y third times y squared over 2. So now this is doable because you can do a u substitution. I hope I didn't get greedy with the space here, because I don't want to move on the second page. So I'm going to do something not so elegant here, but I'm going to emphasize here the u substitution you got to perform here. You have e to y third, y squared here. So obviously you can make a u substitution for y third. Du is 3y squared dy. And now in terms, and the new bounds are still 0 and 1, right? So if y equals 0 and 1, then u is still 0 and 1. So the integral in terms of u is from 0 to 1. E to the u, 1/2 is there. Y squared dy becomes du over 3 from the substitution. So it's just the integral of e to the u with 1/6 on the outside. So it's just 1/6 e to the u between 0 and 1. And when we plug in the bounds, we get 1/6 e to the first minus e to the 0, which is e to the minus 1. I mean e minus 1. So here's a typical example, like I said, which justifies the importance of being able to switch the order of integration. Let's finish the lesson with 2 more examples in which we won't compute anything. We just visualize the domain and just change the order of integration. Basically recalculating the bounds. So stay tuned for the last page. All right, so reverse the order of integration. Let's start with the first one. The integral from 1 to 2, the integral from 0 to natural log of x, and some function to integrate. Like I said, we're not going to compute anything here. We just reverse the order of integration, dy dx. So let me state from the beginning, sometimes occasionally I have a student or two who just basically doesn't, decides not to follow and then goes with the easier way out. Once again, let me state it here, reversing is not this, okay? It's a recalculation of the bounds. It's a problem to be taken slowly and steadily, right? We need to visualize the domain, recalculate the bounds in order to figure out the new bounds in terms of x and y. As given here, the domain means that x is between 1 and 2, and y is between 0 and natural log of x. So let's sketch the domain. We're going to sketch the bounds, basically, right, as curves. So we have y equals 0, which is the x-axis. Visualize the x-axis. We have x between 1 and 2. This is 1 and 2. And we have y equals natural log of x, which looks kind of like that. Y equals natural log of x. I'm sorry, let me actually take it back here, because see, this is the thing. Where does it, yeah, sorry, I got carried away a little bit. Natural log, right? One more time. Let's do it here. One more time. So the natural log goes to the point 1, 0. That's natural log of x. Right? So it goes to the point 1, 0. All right? And then the other bounds, like I said, are y equals 0, which is the x-axis. The curve y equals ln of x equals 1, x equals 2. Okay? So I don't want to fill in inside, but let's again thicken the boundaries of the domain. Okay. It's given as a type 1 domain, right? With x between 1 and 2 on the outside. To change the order of integration, we need to basically start with the bounds for y. Notice again, we need an intersection point. Okay, so the intersection point between y equals ln of x and x equals 2. Pretty straightforward. That intersection point is going to be 2 ln of 2. Right? When x is 2, y is ln of 2. Okay, so therefore the bounds for y, for a typical slice identified by y, are 0 and ln of 2. The inner bounds should be x in terms of y. Look at the leftmost bound for x. What is that in terms of y? I need to get it from the point on the curve, right? The curve is given by y equals ln of x. I need to get x as a function of y. So I need to get x from that natural log. If you exponentiate, x is e to the y. Look how different it looks like, right? It has to be recalculated. So the lower bound for x is going to be e to the y. What is the upper bound for x? That's going to be the same. It's just a constant, right? It goes all the way up to 2 for every slice. So x is between e to the y and 2. So as the conclusion, the integral from 1 to 2 and then from 0 to ln of x of that function dy dx is exactly equal to the integral from 0 to ln of 2 on the outside and then from e to the y to 2 on the inside, but now dx dy. Okay, I purposely chose this example to show you that it needs to be recalculated. If you're not convinced, pick up any function you like and then do it with a computer algebra system in both directions and see that you can, convince yourself that you get basically the same answer for the integral. And one more. Let's say one second here. I want to make 2 square root of 4. Let's do another one. Yeah, let's do one that is type 2 first. So let's say from the integral from 0 to 4, and then from 0 to square root of y. Dx dy. Okay, so let's visualize the domain. So first of all, y is between 0 and 4. And x is between 0 and square root of y. And let's sketch it here. X equals square root of y. X squared. Yeah, x equals square root of y is basically the same as y equals x squared, right? So it's going to be this parabola here. And then x equals 0, which is the y-axis. And then y between 0 and 4. Okay. 0 and 4 here. So the domain in question is this. Let's figure out the intersection point. The intersection point is between y equals 4 and x equals square root of y. That means if y is 4, that means x equals 2. So the bounds for x are actually 0 to 2. This point is 2 and 4. Now, if I want it in the reverse as a type 1 domain, again, I'm going to start with x on the outside between 0 and 2. And then for a given x, I'm supposed to compute the bounds for y in terms of x. So get y in terms of x from the curve here, from the x equals root y. So x equals root y, y by itself is y equals x squared, which goes all the way up to y equals 4. So y is between x squared and 4. And therefore, the same integral is now from 0 to 2 on the outside, x squared to 4 on the outside, dy and then dx. All right, so I think that's enough. Obviously, the homework is a little bit longer because you need to do it. Actually, well, yeah, I lied. There's one one more example I want to go over. So, not the last, just one more example, and that's it. So the last example that I want to go over has to do with the interpretation of the double integral as a volume. So remember, the geometric meaning of a double integral is the volume between the graph of the function itself, which is a surface, and the xy plane, right, over the domain. Again, remember with plus if it's above, minus if it's below, right? But this is essentially, this can be extended to the same concept. Let's say you have basically a solid described by z between two surfaces, f of xy, g of xy. The volume of that solid is going to be the double integral of the top surface minus the bottom surface. This is analogous to calculus 1 stuff, if you remember. Right? Let's say you have, you know, an area which sits between the graph of two functions like that. You don't have to write this analogy, but just to remind you. So the area is just the integral from a to b of the top function minus the bottom function, right? So this is an extension of the meaning of the Riemann integral as the area between the graph and the x-axis in the calculus 1 stuff, right? When you have a single variable function. This is analogous to the same thing. I'm not going to sketch it. Well, maybe we can sketch it here a little bit, but the main idea is that, you know, if you imagine that you have, say, some surface here on the top, some surface here on the bottom, if they happen to project onto the same domain, then you could compute the volume of this object by taking the double integral of the top function minus the bottom function. So a typical example related to this is like this, you know, so find the volume between, let's say, the paraboloid z equals 2x squared plus y squared and the inverted paraboloid 9 minus x squared minus 2y squared. I mean, if you actually imagine how this looks like, these guys look like in a coordinate system, you have basically the paraboloid opened up, right? This one, z equals 2x squared plus y squared. And then another paraboloid opened downward, like that, which is z equals 9 minus x squared minus 2y squared. And you can view this solid as in between these surfaces with the same domain. So where they intersect, and we're going to have to figure out that intersection, projects onto the common domain of these surfaces, right, over the xy plane. So you can view, it's kind of a sloppy here sketch here, but you can view these two paraboloids, if you see them from above, projecting onto the projection of their intersection here in terms of x and y. So in other words, the domain of integration here is wherever these two intersect in terms of x and y. So if I intersect them, I get 2x squared plus y squared equals 9 minus x squared minus 2y squared. If I move everything to one side, simplify by 3, I get the disk x squared plus y squared equals 3. So the domain of integration, if you were to sketch it, is essentially a disk of radius root 3. It's easier to integrate in polar coordinates, which we will do next section, but you can also set it up in terms of the x and y coordinate. So the volume is going to be then the double integral over this domain, top portion, which is the paraboloid open downward, minus the bottom portion, which is the paraboloid open upward. So it will be actually the double integral of 9 minus 3x squared minus 3y squared. We're not going to solve this integral right now because it's easier to set it in polar coordinates. Maybe we can just set Cartesian coordinates and just do it with Maple. Type 1 or type 2 doesn't matter, it's the same idea. So a typical slice, let's say as a type 1, will have x with the bounds minus root 3 and root 3. And the bounds, innermost bounds in terms of x, you need to get it from the equation of the circle. And then don't forget the plus minus when you take the radical. So the bounds for y will be plus 3 minus x squared under the radical minus square root of 3 minus x squared. Like so. And so therefore this, in terms of Fubini theorem, would be the integral from minus root 3 to root 3, integral from minus square root of 3 minus x squared, 3 minus x squared on the top, 9 minus 3x squared minus 3y squared, dy dx. It's gonna be painful to do this with in Cartesian coordinates though, so I'll just leave it at that, and we can solve this more efficiently with polar coordinates next time. All right, so now that's it for today.